We'll discuss gluon distribution. So I did not specify any TMD or GPD or PDF because I do a mixture of different distributions that I will discuss. So these are the main reference, so based on which this talk will be presented. Okay, so we all know that the main goal of PIC is to understand the nucleon structures, not only their special structures, but also their spin and angular momentum and their correlations and all these informations. That is what we want to extract from these PIC experiments. And all these informations actually are encoded in different distribution functions. For example, this form factor, PDFs, generalized pattern distribution function, TMDs, Wigner distributions, and so on. And in last, from yesterday, we are listening talks on PDFs and TMDs. And in this talk, I will also cover some PDFs, TMDs, and also GPDs. And all these distributions are studied in different models because these are mainly non-perturbative objects. So we don't have any first-hand information about from the QCD calculation of these distributions are not available except from lattice. So there are many QCD motivated model results are available, but most of the studies are done for quark distributions. So gluon distributions are not well understood or not investigated in such extent. So this gluon PDFs, we know that they are mainly small x dominated, and in small x, the experimental predictions are also very noisy. So there are a lot of uncertainties in small x, especially for polarized PDFs of gluons, which are not constrained in the small x region yet. And so these are basically some hindrance to actually investigate gluon distributions as such. And except lattice, there are mostly, as I said, that except lattice, they are mostly studied in different models. Okay, so for this lattice, I think you have learned and listened to this lattice talks about that predictions. Anyway, this, so first I will talk about TMDs. Okay, so we assume that TMD factorization, that this SI, for example, here, this SIDIS or say, cross section, you can write as TMD and this hard and this fragmentation function, convolution of these functions. And if you actually, out of this TMD and fragmentation functions, these are non-perturbative objects, and only this hard part that you can do perturbatively. So these two things we have to calculate in some models or from lattice. So, okay, so this TMD actually encode three-dimensional spatial structures of proton because they are function of transverse momentum. And not only they are spatial structures, but they also encode information about their transverse motion, spins transverse momentum correlations, and so on. That is why they become very hot topic in recent times, and especially for EIC in last few years, there are a lot of activities to understand these TMDs. And TMDs are actually in SIDIS and DLEN processes, you can actually access these TMDs. And in experiments, basically, you can actually measure different spin asymmetries which are related to these TMDs, and from there, you can actually extract information about the TMDs. And say, for example, here, one example of this spin asymmetry is that azimuthal asymmetry of unpolarized quarks in transversely polarized proton, that is actually known as Sievert's effect, which is again some T odd function, and they are difficult to access in experiments. But these are actually observed in experiments, these effects. And the explanation comes from the final state interactions where this gluon exchange happens between a struck quark and the remnant of the nucleon. Okay. So EIC can probe this gluon distribution in both polarized and unpolarized proton. And okay, so to study this gluon TMDs, we require high energy or very small x, because at very high energy you can produce a lot of gluons, or at very small x where these gluon PDFs are large. So only in that region you can access them. One of that example is that if you have this EP scattering and you produce back-to-back D meson or gypsy, then you can actually access this gluon TMDs or Siebert function. But these TMDs are not universal because they actually involve on this final state interaction or initial state interaction. For example, in SIDIS you have FSI or final state interaction, but for Drelian you require initial state interactions. And even for quark sector also, these TMDs are actually different for Drelian and SIDIS. And even on top of that, you know that because this gluon part also, this you have this Wilson line because of connecting two different points in this correlator. So there, even for this unpolarized gluon distribution, you have two different definitions of gluon distributions depending on their whether their helicity is flipped or not, right? So these are actually this WW and dipole things. So you actually you can see that different processes and all these things in these papers. And if you want to know more, we already heard talks on this gluon GPTs about their experimental detection and theoretical investigations in yesterday's talks. So we can skip those things here. So what we are actually going to discuss here is that I'll discuss this gluon distribution functions in a simplified model. Okay. So what is that model? So this is basically a spectator model where we consider that gluon is the active parton and rest of the thing is actually a spectator. Okay, so this is a spin half spectator. So this is a very simplified model, but even in very oversimplified model also, when you cannot do QCD calculations, these models predictions give you very intuitive insights and help you to understand the underlying physics. So simplicity is not that so to actually disregard that. So here basically what we do is that you have this model where you have this spin half spectator and this gluon is the active parton. So that proton state, for example, with spin up and down, you expand in the all possible combination of their quark and this gluon spin combination. So here this first index is for the gluon helicity and the second one is for the quark, and this up, so the superscript are actually for the proton. So these are the wave functions corresponding to the different sectors of this state. So this model was first proposed by Veketa and their groups. But here what we do actually is that we use these wave functions actually that we take construct this wave function from some ADS-QCD predictions. So we modify that ADS-QCD predictions, and here basically this wave function, one of a few wave functions are written here. So this phi that is sitting here, So that is written like this. So this wave function, if you just put this B and A 0, then this actually goes to ADSQ-CD2 particle wave function prediction. Okay, so we modify this wave function with these parameters A and B, and this Ng is some normalization constant. And here you have this spectator mass Mx. So these are the parameters that are actually in this model. And these model parameters are fitted with the unpolarized gluon PDF with the NN PDF data at Q square is equal to 2G. So as I said that there are only 4 parameters in the model, A, B, and Ng and this Mx. So this Ng is the normalization condition. So that you get from the normalization of the distributions. And for the stability of that model, you require that spectator mass Mx has to be greater than Mx so that this spectator and gluon state does not decay into proton. And so basically the behavior of the distributions, they actually determined by these 2 parameters A and B. And these 2 parameters actually, so these parameters are fitted by unpolarized gluon PDF that we take from NNPDF 3.0 NLO data. So from our model, we can actually extract this unpolarized PDF for gluon. So this is basically the analytic expression. So from here, you can see that basically this behavior of these functions is basically determined by these 2 A and B, mostly. Okay. Other parameters, so this Mx has very small effect on this overall behavior, and this is the overall normalization constant. So here is basically that fitting of these parameters. So this magenta is actually from NNPDF, and blue is from our fitting. So we actually fit with the middle value, and here actually consider 100 replica of NNPDF data. And as we have heard this discussion that for very small x, gluon TMDs or gluon PDFs are uncertain. There are large uncertainties in the small x region, so we don't fit to very small x. So our fitting is only for 0.0012 x in that region. Even in that region, you can see that lot of uncertainties are there. So basically, except this unpolarized gluon PDF, everything else, whatever we calculate is our actually prediction. And here, for example, in this model, when we calculate the average longitudinal momentum, that x average, that actually we get around 0.416, whether this lattice result is 0.427. It is pretty close to that lattice prediction, though our model is very, very simple compared to the lattice calculus. So here actually you show this gluon helicity PDF. In this case, you can see that gluon helicity PDF has a lot of uncertainty even from this NNPDF data. And our model actually overshoots in this region. So, but if you just see that with these different experimental measurements of this ratio, that G1L versus F1, then this data is concentrated mainly in a very small region of X. So it is in that ballpark, but to pinpoint that thing is very difficult. And this black is actually from this result, but I think that is also fitted data, not prediction in your paper, in that paper. So from this gluon, from helicity GPDs, we can calculate the total gluon spin contribution. So that you get from this integration of this, sorry, it is actually G1. Okay, so sorry for the different notation. In different region of X, we actually integrate, because in different groups they have in different range, not for whole range. This result is not available. So it is almost in the ballpark with different things, but when we actually integrate over this from 0.05 to 1, then our prediction is large, and that large, why you can see that because of this, it is overshooting here, so that actually shows up here also that it is large. But anyway, they are comparable to the other models or other calculation and even in PDF. So here are other PDFs. Again, you can see that large uncertainty is there. And this actually compared with another spectator model. But in their model, it is sharply falling, but in our case, it is not so sharp. So this actually depends on the model parameters, so you cannot exactly say that which one is better or worse. So once you actually fit all these PDFs, so and your parameters are now fixed, then you can actually go into the TMDs. Okay. So this Gluon TMD, you can actually for SIDIS, you can write like this, and there are, if you expand in that thing, you can just get 4 T-even TMDs and 4 T-odd TMDs. So these are all discussed in talks yesterday. Okay. So let us first discuss the unpolarized TMD, F1G. And this, in the wave function representation, in the light cone overlap representation, you can write like this. And that actually gives you this expression. Okay. And when you integrate this TMD, you get the unpolarized PDF that you can check that it is actually producing. And similarly, you can actually calculate this helicity TMD, which actually gives you the circularly polarized gluon in longitudinally polarized proton. Okay. And again, you can actually use this light cone overlap representation to extract that functions. And again, when we integrate over this p-part, it goes to the helicity PDF. And worm gear TMD, that actually gives you circularly polarized gluon in transversely polarized proton. And again, you just get that expression, analytic expression for that TMD. And both of these things, when you integrate, so that we have discussed. So here this Boyer-Mulder's TMD, that is for linearly polarized gluon inside unpolarized proton, which actually involves interference between this plus minus gluon helicities. And that again has this expression. So when you integrate over their transverse momentum, you get the corresponding PDFs. So these are basically 3-dimensional plot of the TMDs, and these are some 2D for fixed X values. How does it look like? So these TMDs satisfy some positivity bounds, okay, or some relations or some constant. So these are actually called this unpolarized TMD has to be greater than 0, and that has to be greater than also mod of G1L. So this polarized, unpolarized TMDs has to be larger than the polarized PDFs. And even this Mulder's-Rodriguez relations, they are more stringent than this positivity bound. Okay. And all these relations are actually satisfied in our model, and even without explicit values of the parameters. In the wave function level, all these constant you can satisfy. So for example, here you have shown this positivity bound. So this basically, this last relation that you can actually see here, that for different X values, this positivity bound is, so ratio has to be less than 1. But as you actually go to very, very small x, this positive bound actually saturates and it becomes 1 quickly. But as you go away from for larger x, it never saturates, at least for any reasonable value of p power. So the saturation occurs only for small x. Now from these TMDs, we can actually see that gluon densities. So for example, this unpolarized gluon density in unpolarized proton that actually gives by this unpolarized TMD. And this is the picture of this distribution. You can see that this is cylindrically symmetric distribution about x, yeah. So that is expected because they both are actually unpolarized. So this distribution is completely symmetric. But when you consider Boyer-Mulder's density, then longitudinally polarized gluon density. So this is again spherical symmetry actually get distorted by this second term. And that you can actually see that this second term actually, it looks like some dipolar structure. That creates the distortion. And this result is also again comparable to this result in that paper. And here basically this helicity density, again it is circularly polarized gluon. That density in a longitudinal polarized proton. And this again for this worm gear density, you circularly polarized gluon density in a transversely polarized proton. And in this case, you see that since this is longitudinally polarized proton, in that case, you still have this cylindrical symmetry of the distribution. But when you have this transversely polarized proton, that distribution actually got distorted, okay, and the cylindrical symmetry is broken. So that actually better seen from this two-dimensional plot, that here this value of this density is less than this. So you get a left-right asymmetry. Okay, now let me go to GPDs. So these generalized Proton distributions, they actually appear in the exclusive processes. So these TMDs appear only in the semi-inclusive DIS, but these GPDs actually they appear in the exclusive processes like this deeply virtual Compton scattering or vector meson production. So one of this is a diagram of DVCS where actually you can actually access these GPDs. So these are upward matrix element because this momentum of this incoming proton and the outgoing proton are not same. This gluon actually, this photon exchange some momentum to the proton. So they are function of 3 variables, that x, and this zeta is called the skewness. That is basically the fraction of longitudinal momentum transferred in the process. And the total T is the total energy, momentum transfer square. So they also encode spatial information as well as spin structure of the nucleon, but they don't have probabilistic interpretation because they actually are the matrix element between the proton with 2 different momentum states. So you cannot actually give any probabilistic interpretation there. But for zero skewness in the impact parameter space, so basically if you take the Fourier transform with respect to the momentum transferred, you get these GPDs in the impact parameter space, and then you can actually have some probabilistic interpretation. And for in the forward limit, this GPD is again reduced to the PDFs. So these are the constants you can actually check for your calculation. So again, so these are basically the how you actually expand these correlators and you get different GPDs. Okay, so these are the helicity conserving GPDs, H, E, and H tilde and E tilde, And there are 4 helicity flip GPDs or non-conserving, that HT, H tilde T, ET, and E tilde T. So all these things are actually in the light cone gauge that we have. Okay, so in this work, we will consider only in certain region of kinematical region where x is greater than zeta, xi, so that a quark and longitudinal momentum fraction x plus xi gets hit by a photon and comes back to the proton with x minus xi. So basically, you have this number conserving process. And as I said that these GPDs are actually goes to the PDF in the forward limit. So these are some 3-dimensional picture of the GPDs. Out of this total 8 GPDs, only 6 are actually non-zero in our model. And these are basically 2-dimensional depiction of the same 3-dimensional GPD pictures for different skewness zeta. Well, so as I said that the GPDs in the momentum space don't have any probabilistic interpretation. So to have some probabilistic interpretation, we need to go into the impact parameter space. So if you take this Fourier transform with respect to the momentum transferred and xi is equal to 0, that skewness is equal to 0, then only you can actually have the probabilistic interpretation for these GPDs. Okay. And this B perf here, that actually gives you the transverse distance of the stack quark from the center of momentum. For example, this B perf square, that actually gives you the size about the transverse size of the nucleus. So at small x, what we found is that gluon actually has larger transverse radius than quarks. But as you actually x increases, that radius actually shrinks, and at x is equal to 1, it becomes like a point. So that you can actually see from these plots. So here are the impact parameter dependent GPDs, and as you actually decrease x, you can see that they are actually growing. So for large x, they are actually this impact parameter, they become 0 very quickly. Okay, and this is true for all these GPDs. Now these GPDs, from here actually you can extract this angular momentum that we saw today in the morning, that by this G sum rule, you can actually extract from these GPDs the angular momentum. And what we actually get from our model is 0.058, that is the gluon contribution. And this BLFQ basis light front quantization calculation of the same quantity actually is this. So they are very consistent with each other. And as we know that this helicity GPD gives the spin contribution. So if you just deduct that part, you will get the orbital angular momentum, that you actually say that kinetic orbital angular momentum. And in our model, it looks like this x dependence of that orbital angular momentum. And if you integrate, it gives you minus 0.18. Again, another model calculation is in the same ballpark. But another way of defining this angular momentum, that is called canonical angular momentum, that you can actually define through GTMDs. And okay, so this in the next, I just have a little bit discussion about GTMDs. So GTMDs are higher dimensional distributions, so they are not experimentally measurable. So they are actually Fourier transform of these GTMDs are actually related with the Wigner distributions. These are basically 5-dimensional phase space distributions. But these are actually called the mother distributions of all these TMDs and GPDs, because in different limits of these GTMDs, you can extract TMDs and GPDs. For example, TMDs can be obtained from the GTMDs at delta parp tends to 0 limit. And whereas when you integrate over this P parp, you will get the GPDs. And this GTMD correlator actually written like this for zeta is equal to 0, sorry, this skewness xi is equal to 0. So here again, you can see that this initial and final state, they are actually differ by this momentum. And this GTMD, say F1,4, you can actually write like this in the right cone overlap formalism. And that describes the distortion of the unpolarized proton in a longitudinal polarized nucleon. And similarly, this G11, that is another GTMD that gives you the distortion of longitudinal polarized gluon inside a unpolarized nucleon. And from there, I can actually define again this canonical orbital angular momentum. And that canonical orbital angular momentum, I can actually get like this. This is the analytic expression. And if I plot, you can see that this is completely different from this. Okay. So this was the kinetic orbital angular momentum, and this is canonical orbital angular momentum. But if you integrate over x, so the total value, from here you get minus 0.19, and from here it is minus 0.18. So very close in this model. They are almost equal. And again, from this G11, we get this spin orbit correlation. So this is actually proposed in this paper. So if this C factor that you get is negative or less than 0, then the spin and orbital angular momentum are anti-aligned. And when it is positive, then you can say that spin and orbital angular momentum are aligned. And in our model, we actually get this gluon orbital angular momentum and spin are actually anti-aligned. Okay, so let me finish with the summary and conclusion. So to understand the three-dimensional structure and partonic level description of the spin and orbital angular momentum, we need to investigate both quarks and gluons. Not only quarks and gluons, so you also need to understand the C quark contribution too. And there will be one talk on this C quark also. Yes. And these gluon distributions are not yet well understood or studied, so we need to put more effort to understand that gluon distributions. Otherwise, the complete structure of the proton will not be understood. And in this talk, we presented some gluon distribution in a simple model. And from there, we also predict this gluon contribution to spin and orbital angular momentum and their correlations. But definitely, we require more experiments. And I think where EIC is going to play a major role. And lattice results, and also we require better model building to understand the gluon distribution. Thank you.
Questions, comments? Elke?
Yeah, no, thank you for the nice summary. I have a question. Your delta G, have you used data or it's a pure prediction?
It is pure prediction.
Okay, okay, good. So it's clear because...
only unpolarized PDF that we fit.
Okay,
nothing
perfect.
else.
And from there you derive it through the model, how you
Yes,
have
yes.
the dependencies. Okay, perfect, I understood. Thank you.
Can you hear me? Yes. So a comment and a question, or two comments. So one thing is that maybe you didn't emphasize it, but if I am not wrong, your unpolarized TMD, similarly to what happens in our case, does not have a Gaussian shape, but starts from very small, then grows, and then goes down, right?
Yes.
So you confirm this feature, which is probably typical of spectator-like models, but okay, you confirm it. Yeah. That's interesting. And the second thing is related to Elke's question. So you fitted only the unpolarized, but can you try to play around with parameters and also fit the helicity distribution?
Yeah, that can be done, obviously, but you wanted to fit all these parameters because only unpolarized can fit, because we have only 4 parameters, right? And one is normalization, so that is not actually playing any role in the shape. And this spectator mass is also plays very little role in the shape. Only this A and B, these 2 parameters that we have. So they are the parameters that we need to fit, and that we can fit from unpolarized PDF only. Okay, we don't require to do that thing. So we can do that definitely by fitting these polarized GPDs also.
Yeah, because, okay, yeah, and as you were discussing, basically the most relevant parameters are these A and Bs.
Yes.
Which unfortunately are not in the ADS QCD predictions.
No.
These are exactly the part that you had, which are different. But anyway, could you maybe try to...
No, but these exponential terms actually play...
those are
important
okay,
role.
but the x to the alpha, 1 on x to the A, 1 on x to the B is an additional term
Yeah,
that you
so
put.
these are basically for this endpoint.
Right. No, I was thinking if you can put these extra terms on differently on the life from wave functions.
Yes.
So I have 4 parameters instead of 2, then you can definitely also have a different helicity.
Yeah.
Yeah, there is other parameter, the kappa, in the transverse directions, but we didn't fit that. That is taken from the previous study. And A and B, if we set A and B, that will give you these ADS-QCD predictions. But ADS-QCD just considering the transverse direction, no longitudinal directions. So you have to solve longitudinal dynamics for that. So we don't do that. That's why you use this exponent, x to the power A and 1 minus x to the power B term. So, if we solve like 2 free equations, if we solve 2 free equations, we have some longitudinal dynamics for that. So since we are considering this transverse dynamics from ADS-QCD, that is from our model development.
I have just one more question. You fit only to DIS data if you fit.
Yes.
Yeah, and then you cannot do the G1 as a helicity one because the DIS data don't constrain a delta G at all. That's because of the Q square X range, which is there. It's basically impossible.
Yeah, because helicity has also a lot of uncertainties also, right?
Yeah, it's just, we have shown this a long time ago with DSS3. If you take only the DIS data, you don't get a delta G constraint at all. So you need to see, with the EIC data that would work, but not with the current existing one.
So yeah, our fitting is basically from this in PDF data.
Other questions? Asmita.
Yeah, just one question. So LK, are you suggesting that actual better method would be just to take the more number of parameters instead of taking only A and B and fit both the unpolarized PDF and the helicity?
No.
That is Alessandro's proposal.
But that was Alessandro's proposal. I was saying that fitting right now, taking the DIS data and trying to get delta G out is impossible because the XQ square is not large enough. You don't get a constraint on delta G.
Yeah, so in that case, what Alessandro was suggesting, that would be better?
I doubt it.
Okay, so my suggestion was just to increase the number of parameters and try to describe also G1, but concretely speaking, if you had to do it like this, what I would do is what we also have done in our paper. We would take already the extraction of delta G from the global feeds and then reproduce that, not compare directly with the data. Right.
Okay. Other questions? I have a question. Is in your, for example, in the Gluon TMDs, do you include TMD evolution? In your
No, we have not included evolution
so
here.
they are given at a
At
fixed
the
scale.
initial scale.
And, okay. So they are publicly available.
Yes.
The parameters are in the paper and one can.
Yeah, one can put that evolution, and we have not done that here.
you very much.